There's a spacecraft right now, at this very moment, traveling through a region of the solar system that no human instrument has ever properly mapped. Moving so fast it covers the distance between New York and Los Angeles in under 4 minutes, and it is sending back data that is forcing planetary scientists to tear up some of the most fundamental assumptions they had built about where our solar system ends. It has been flying for over 20 years. It is roughly the size of a grand piano. It runs on a nuclear battery the size of a fire hydrant. And what it has been finding out in the cold dark beyond Pluto isn't what anyone expected. Not even close. This is the story of NASA's New Horizons spacecraft, what it photographed past Pluto that genuinely shocked the scientists who built it, what it discovered about our solar system that shouldn't have been there according to every model. Astronomers had spent decades constructing, and why the implications of those discoveries reach far beyond a single spacecraft in the outer dark, all the way to how we understand the architecture of the solar system itself, and what might be hiding in corners of it we have never been able to see. To understand why what New Horizons found is so significant, you first have to understand what scientists expected to find when they sent it out there, because the gap between what the models predicted and what the instruments actually measured is where the real story lives. The Kuiper Belt, the vast region of frozen rocky debris that extends outward from Neptune's orbit at roughly 30 astronomical units from the Sun, has been known to exist since 1992, when astronomers at Mauna Kea in Hawaii first directly detected one of its objects through a telescope. In the decades since, ground-based surveys had detected more than 1,000 of these Kuiper Belt objects, or KBOs, and constructed what seemed like a fairly confident picture of the belt structure. It was generally thought to extend from about 30 AU to approximately 50 AU from the Sun, where AU stands for astronomical unit, the average distance between Earth and the Sun, about 150 million kilometers. At 50 AU, the model said, the density of objects should begin dropping off sharply, thinning out toward the relative emptiness of the distant outer solar system. This outer boundary was considered reasonably well established. Not certain, but well established. D. The belt gets less dense at 50 AU. That was the model. That was what decades of telescope work had suggested. And when New Horizons launched in January 2006 with a small but sophisticated dust counter aboard, among other instruments, one of the things nobody was particularly worried about was encountering unexpectedly high dust levels past 50 AU, because the model said the dust should be thinning out there, not building up. The model was wrong, and the way it turned out to be wrong is the kind of result that keeps planetary scientists up at night staring at data printouts, wondering what else they have missed. New Horizons launched from Cape Canaveral in January 2006, already the fastest spacecraft ever sent from Earth at that point, moving at a speed that carried it past the moon's orbit in just 9 hours, a journey that took Apollo astronauts 3 days. By February 2007, it had used Jupiter's gravity in a flyby that boosted its speed further, slinging it outward toward Pluto at over 57,000 kilometers per hour. It spent nearly a decade crossing the solar system, flying through cold, dark, largely empty space. And then on July 14, 2015, something happened that most of the scientific community had been waiting their entire careers for. New Horizons swept past Pluto, coming within 12,500 kilometers of its surface, close enough that the cameras aboard could resolve features on the surface the size of small towns. And what those cameras showed was one of the most complete scientific surprises of the 21st century. For the 8 decades between Pluto's discovery in 1930 and the launch of New Horizons, humanity had exactly one view of Pluto, a blurry smudge. Even the Hubble Space Telescope, for all its power, could resolve Pluto only into a handful of indistinct pixels, showing vague variations of light and dark. Scientists assumed, based on completely reasonable logic, that Pluto would turn out to be geologically dead. It is small, less than 2/3 the diameter of Earth's moon. It orbits the Sun from an average distance of about 39 AU, where sunlight arrives about 1,600 times weaker than it does on Earth. It has no large neighboring planet to exert tidal forces that could keep its interior warm. By all reasonable expectation, it should have frozen solid billions of years ago and done nothing geologically interesting since. The first images that New Horizons sent back in July 2015 showed something that made planetary scientists openly emotional with shock. Pluto was alive. Not biologically, but geologically, dynamically, actively alive in ways that violated every prediction the models had made about it. The first thing anyone noticed was the heart. An enormous, bright, heart-shaped feature spanning roughly 1,600 kilometers across the face of Pluto, later officially named Tombaugh Regio in honor of the astronomer Clyde Tombaugh, who discovered the dwarf planet in 1930. The left lobe of that heart, a vast plain called Sputnik Planitia, turned out to be the largest known glacier in the solar system, a nitrogen ice sheet sitting inside an ancient impact basin, its surface covered in polygon-shaped convection cells, where warmer ice from below slowly rises and cooler ice sinks in a cycle that continuously renews the surface. The surface of Sputnik Planitia is geologically young, perhaps just a few million years old at most, meaning Pluto has been actively resurfacing itself in cosmically recent times. This is a world in the outer dark, billions of kilometers from the sun, where the temperature sits at negative 229 degrees Celsius and it has a heartbeat. The nitrogen ice in Tombaugh Regio cycles between subliming into vapor during Pluto's long day and condensing back to ice during its frigid night. And that daily cycle drives actual winds across the surface of a world with an atmosphere only 100,000th the density of Earth's. Pluto's literal heart, it turned out, controls Pluto's atmospheric circulation. Rising around the edges of Sputnik Planitia were mountains of water ice, peaks jutting 3,500 meters above the surrounding plains, as tall as the Rocky Mountains, standing on a world where water ice is so cold it behaves like solid rock. Blade-like spires of methane ice rise across other regions of the surface, taller than New York skyscrapers, created by a process of sublimation and redeposition that carves the landscape in alien patterns that have no direct equivalent anywhere else in the solar system. There are ancient riverbeds and lakebeds carved by flowing nitrogen in Pluto's geological past. There is a dark reddish polar cap on Pluto's largest moon Charon, created by atmospheric gases escaping from Pluto and freezing onto the surface of its companion world, 1.5 billion kilometers away. The 4 smaller moons of Pluto spin so rapidly they have become geologically unstable, tumbling chaotically in ways that defy the expectations of tidal locking that govern almost every other moon in the solar system. And the data from New Horizons hints that beneath all of this, beneath the nitrogen glaciers and the methane spires and the water ice mountains, Pluto may harbor a liquid water ocean, kept from freezing by a combination of internal heat and the insulating properties of the ice above it. Pluto, the world that was demoted from planet to dwarf planet in 2006, the world that was supposed to be a frozen, dead, geologically boring relic of the early solar system, turned out to be one of the most geologically complex and surprising worlds the human species has ever examined. Alan Stern, the chief scientist of New Horizons, said after the flyby that they had found a world that rivaled anything else in the solar system for complexity. He wasn't exaggerating. The data from the Pluto flyby took over a year to fully transmit back to Earth, because at that distance, sending information home at the speed of light still takes 4.5 hours one way, and New Horizons was transmitting through a connection that made a dial-up modem look fast. But even while that data was still trickling in, mission controllers were already looking beyond Pluto, because New Horizons still had fuel, still had power, and still had all 7 of its scientific instruments functioning. The question was what to point them at next. After an intensive search using the Hubble Space Telescope, astronomers identified a candidate deep in the Kuiper Belt, a small, reddish object they designated 2014 MU69, orbiting the Sun at 44.6 AU, roughly 1.5 billion kilometers past Pluto. It would require a precise series of course corrections to redirect New Horizons for a flyby. The target was so faint that scientists couldn't even determine its size or shape before the encounter. What they knew when they aimed the spacecraft at it was only that it was there and that it was reachable. On January 1st, 2019, New Horizons flew past that object at a distance of just 2,200 miles from its surface, and what the cameras captured was something that sent the planetary science community straight back to the drawing board. The object, later officially named Arakoth, turned out to be a contact binary, 2 separate lobes of ice-rich material that had once been distinct objects slowly orbiting each other and had eventually drifted together and merged, their surfaces now touching along a narrow neck connecting the larger lobe, nicknamed Ultima, to the smaller one, nicknamed Thule. The result looks remarkably like a flattened snowman. At 35 kilometers long, it is far smaller than any world New Horizons had previously visited, and that small size combined with its extreme distance from the Sun means that Arakoth has been sitting in essentially the same orbit, essentially unchanged, since the solar system was forming 4.5 billion years ago. It is, in the most literal scientific sense, a fossil from the birth of our solar system, a primordial planetary building block preserved in the cold dark of the Kuiper Belt for billions of years without the gravitational disturbances, collisions, and chemical alterations that have processed and modified every object in the inner solar system beyond recognition. The shape of Arakoth told scientists something they had been debating for decades about how planets actually form. The 2 lobes came together slowly and gently at low relative velocities, indicating they had formed close together from the same collapsing cloud of material rather than having been thrown together by a violent, high-speed collision. This gentle, local assembly process, called pebble cloud collapse or streaming instability, was confirmed by Arrokoth's shape in a way no laboratory experiment or computer simulation could have provided on its own. One object, visited once, briefly, resolved one of the most fundamental open questions in planetary formation science. Arrokoth remains the most distant object ever explored by a spacecraft. And every bit of data from that encounter is still being analyzed, still producing papers, still changing what scientists understand about how the solar system was assembled. And then New Horizons kept flying. Past Arrokoth, past the edge of the known Kuiper Belt, out toward 50 AU and beyond, where the models said the dust should thin and the solar system should begin its quiet fade into interstellar space. The spacecraft has a small instrument aboard called the Venetia Burney Student Dust Counter, or SDC, designed and built by students at the University of Colorado Boulder. Its job is exactly what the name suggests, counting dust grains that impact the spacecraft as it moves through space, measuring the density of interplanetary dust as a function of distance from the Sun. As New Horizons moved through the main Kuiper Belt between 45 and 50 AU, the SDC behaved more or less as expected, counting dust at levels consistent with the model's predictions for a region full of colliding and eroding Kuiper Belt objects. And then something strange happened. New Horizons crossed 50 AU. According to the model, the dust should have begun to thin. Instead, the SDC kept reading elevated dust levels. Past 50 AU, past 55 AU, approaching 60 AU, the dust counter was still registering impacts at rates that the model said should not be there. The data was published in a paper in the astrophysical journal Letters in February 2024, and the conclusion was simple and staggering. Something is out there past where we thought the Kuiper Belt ends. Something is producing dust. And whatever it is, the models didn't predict it. Alan Stern, the principal investigator of New Horizons, said in April 2024 that these new scientific results may be the first time that any spacecraft has discovered a new population of bodies in our solar system. Let that settle for a moment. A new population of solar system bodies? Not a new asteroid or a new comet or a new moon around a known planet. A new population of objects, an entirely uncharted collection of material orbiting our own sun, whose existence we did not know about because no instrument has ever been in a position to detect it directly, and whose presence New Horizons detected purely because it happened to be flying through the region and had a dust counter running at the time. Simultaneous ground-based observations using the Japanese Subaru telescope have found individual Kuiper Belt objects at distances well beyond 50 AU, some potentially as far out as 80 AU from the Sun, 30 astronomical units past where the main belt was supposed to end. Pontus Brandt, the New Horizons project scientist at Johns Hopkins, put it plainly after the spacecraft woke up from its planned hibernation in June 2026. New Horizons has traveled beyond the known boundary of the Kuiper Belt, and it's still in a dusty environment. He added, with the understated excitement of a scientist confronting data that breaks his own models, that he has a hunch they have just scratched the surface of what the entire solar system really looks like. The implications of an extended Kuiper Belt, or potentially a second belt entirely, ripple outward in several directions simultaneously, and each one is consequential for how astronomers think about both our solar system and the planetary systems forming around other stars throughout the galaxy. The Kuiper Belt is understood to be the outer solar system's analog of the debris disks observed around other stars through telescopes. These disks, glowing in infrared light that telescopes like the Hubble and the James Webb Space Telescope can image from Earth, represent the leftover material from planetary formation that was never incorporated into planets, comets, or major objects. The structure, extent, and density of a star's debris disk tells astronomers something about the history of that planetary system, about what kinds of planets formed, how they migrated, and what gravitational events shaped the distribution of material in the outer reaches of the system. If our own Kuiper Belt extends significantly further than the models predicted, and if there is an additional population of objects beyond it, that tells astronomers something about the history of our own planetary system that the current models have been missing, and it potentially suggests that debris disk models used to interpret observations of other star systems have been systematically underestimating the outer extent of those disks as well. The solar system, in other words, may be bigger and more structured in its outer regions than humanity has understood for the entire history of astronomical observation. There's also a direct observational dimension to what New Horizons has found that goes beyond the dust counter results. The spacecraft's long-range reconnaissance imager, called LORRI, is capable of photographing distant Kuiper Belt objects from angles and at distances that are simply impossible from Earth, including at very high solar phase angles, where the way sunlight scatters off a surface tells scientists about its texture and composition. As New Horizons moves through the outer Kuiper Belt and potentially into whatever lies beyond it, LORRI is systematically observing distant KBOs as it passes through the region, building up a catalog of measurements that can only be made from inside the belt, not from the comfortable distance of Earth orbit. The Vera Rubin Observatory in Chile, which became operational in 2025 and represents one of the most powerful ground-based survey instruments ever built, has been pointed at the region ahead of New Horizons, with the specific goal of searching for new objects that might be detectable by LORRI as the spacecraft approaches them, potentially even finding a third flyby target if one can be identified far enough in advance for a course correction to be made. The search is, as Stern described it, looking for proverbial needles in the cosmic haystack. But the payoff, if one is found, would be another contact with the primitive solar system that only New Horizons can provide. And while all of this is happening in the outer Kuiper Belt, New Horizons is simultaneously conducting science that has nothing to do with the belt itself. Measurements that place it in a unique position, shared only with the 4 Voyager and Pioneer probes that preceded it into the outer solar system. The spacecraft is measuring the structure of the heliosphere, the enormous bubble of solar wind particles that surrounds our solar system and extends outward until it meets the interstellar medium. The boundary where the solar wind slows to a stop and interstellar space begins is called the heliopause. And New Horizons, unlike the Voyager spacecraft that crossed it decades ago, carries modern instruments sensitive enough to take measurements of the charged particle environment, the ultraviolet background, and the interstellar dust flux in ways that could not be done with 1970s technology. Scientists using New Horizons data reported in 2026 evidence of unexpected heating of interstellar particles in the outer heliosphere, a finding that suggests the boundary region between our solar system and interstellar space is more dynamic and more complex than the Voyager measurements alone implied. The spacecraft's ultraviolet spectrograph is mapping interplanetary hydrogen and searching for signatures of the hydrogen wall, a feature at the heliopause where interstellar hydrogen piles up against the edge of the heliosphere. A measurement that has implications for understanding how our solar system interacts with the interstellar medium that permeates the galaxy. New Horizons is also measuring the cosmic optical background, the diffuse glow of light filling the universe from all directions, which turns out to be dimmer than expected, a result published in 2021 that has prompted debate about whether there is more light in the universe from sources we cannot individually resolve than current models of the galaxy's star count can account for. What makes New Horizons exceptional among human spacecraft is not any single discovery it has made, as remarkable as each of those has been. It is the combination of what it has seen and what it is still seeing. The fact that a machine launched 20 years ago with technology that was already mature by the time it flew is still in excellent health, still producing new discoveries at a rate that surprises the scientists who built it, and still flying into territory where no human instrument has ever been before. Its plutonium-powered nuclear battery is expected to keep it functional into at least the 2040s, by which time it will be more than 15 billion kilometers from the Sun, approaching or already through the heliopause, and its instruments will be measuring the environment of genuine interstellar space for the first time in human history with tools sophisticated enough to answer questions the Voyager probes were never equipped to ask. The solar system, it turns out, does not end where we thought it did. The Kuiper Belt, the great outer boundary region that New Horizons was designed to explore, extends further than the models predicted, is dustier at its outer edges than it was supposed to be, may contain an entirely unknown second population of objects beyond the first, and is still actively being mapped by the only spacecraft humanity has ever sent through it. Pluto is geologically active when it was supposed to be dead. Arrokoth is pristine in a way that answered fundamental questions about how planets are built. And the dust counter on a spacecraft originally designed and funded to fly past Pluto is, several years past that flyby, still counting impacts in a region where the solar system was supposed to be running out of things to count. The something that New Horizons found past Pluto that shouldn't be there isn't a single object or a single measurement. It's an entire extension of the solar system we didn't know existed, being revealed for the first time by a piano-sized spacecraft running on plutonium, flying alone through the dark at 50,000 kilometers per hour, and still sending home data every single day.